everyone, my name is IZZY BELTRAN, and for today's report, we're focused on one thing: how to solve static equilibrium problems. Here is our learning points. First, what is static equilibrium? Second, the conditions for static equilibrium. Third, solving static equilibrium problems. So, what is static equilibrium? Static equilibrium is a state where an object is at rest and the net force acting on it is zero. This means that the sum of all forces acting on the object is balanced, resulting in no acceleration or movement. Here's an example of static equilibrium. First, a picture hanging on a wall. Gravity pulls the picture down. The tension in the string and the support from the nail pull or push upward and balance the downward pull of gravity. Since the picture is not moving, the forces acting on it are equal. Because the forces are balanced and the object is at rest, the picture is in the state of static equilibrium. Another example of static equilibrium: a person sitting on a chair. The force of gravity pulls the person downward. The chair pushes upward with an equal and opposite force. If the person stays still and the chair doesn't move, the forces are balanced and the system is in static equilibrium. Here's the conditions for static equilibrium. For an object to be static equilibrium, two conditions have to be fulfilled. Translational equilibrium or no net force requires no net force, meaning the sum of all forces is zero. This prevents linear acceleration. Rotational equilibrium or no net torque requires no net torque, meaning the sum of all torque is zero. This prevents angular acceleration. The problem asks for the normal forces, Nx and Ny. On a 10 kg box supported by a wall and floor, since the box is not moving, it is in static equilibrium, meaning the sum of forces in both the x and y direction must be zero. First, we need the weight of the box. Weight equals m times g. 10 kg times 9.8 meters second squared equals to 98 Newton. In the vertical direction, the upward force must equal the downward weight. Therefore, Ny is equal to 98 Newton. In the horizontal direction, the box is simply resting against the wall. There's no force pushing it into the wall. Since the net horizontal force must be zero, the normal force exerted by the wall, Nx, is 0 Newton. So, our final answer is the normal force exerted by the wall, Nx, is 0 Newton, and the normal force exerted by the wall, Ny, is 98 Newton. Here's another problem solving. A 40 kg child sits on a seesaw 3 meters away from the pivot point. The mass of the bar is 10 kg. Where should a 30 kg child sit to balance the seesaw? What is the normal force exerted by the pivot point? So, for the seesaw to be in equilibrium, the upward force must equal all the downward weights. We add the mass of all three objects. 40 kg plus 30 kg plus 10 kg is equal to 80 kg. We multiply this total mass by gravity, 9.8 meters second squared. So, the upward normal force is 784 Newton. For the seesaw to balance, the torque on the left must equal the torque on the right. Remember, torque is calculated as force times distance. Left torque, the 40 kg child is 30 meters away. Right torque, the 30 kg child is at a known distance or x. We said that turning forces equals to 30 times x equals 40 times 3. Solving for x, 120 divided by 30 equals 4. The 30 kg child must sit 4 meters away for it to balance. So, in summary, the normal force exerted by the pivot is 784 Newton. and the 30-kilogram child must sit 4 meters from the pivot to balance the seesaw.